Awesome. So today I'm going to talk about what practical notions of safety could look like in close proximity human-robot interaction. So whether we're talking about robot navigation around people or human-robot collaboration, the ability to anticipate what people will do is really critical for interaction. So these days, anticipating human behavior is often tackled by using high-capacity end-to-end models that take in the raw scene and output predictions, either in isolation or conditioned on what the robot plans to do. So here's an example of such a predictor at work in a busy roundabout. Each red dot is a car, and the model is generating a prediction for one of these agents. The predictions are in black, and the ground truth is in blue. And as you can see here, they're really spot on. Unfortunately, though, these end-to-end predictors aren't perfect. They typically work only when we've seen a lot of training data similar to the new inputs that we're evaluating them on. So if there's distribution shift, then all bets are off. Here we're going to be testing that same predictive model in a situation where the agent uses a new exit from the roundabout that was never seen before at training time. The predictive model has access to the route information. So if it actually learned how to follow the route and stay on the road and not crash, it should be able to predict this new situation. Instead, here's what we see happening. The model keeps insisting that the agent will go right instead of following along. And here you see the predictions in black compared to the ground truth in blue. What's really funny here is that it's actually predicting the agent to exit at a location that's not even a real exit. So once the agent passes that point and it starts predicting that the agent will plow right through the middle of the roundabout and go off the road. We see a similar situation happen here in the navigation domain, where we have a quadrotor making predictions about where a human's going to walk towards. However, there's some coffee spilled on the ground, but this predictive model does not know that we humans don't like stepping on a coffee because that had never happened before at training time. And so here what we end up seeing is the predictions are systematically erroneous, causing the robot to collide head on with the human. And so we're faced with the fact that data-driven models of people will fail sometimes, compromising the safety of human-robot interaction. But how do we actually achieve safety? So robust control theory would have us treat the person as a disturbance. They might do anything. And what this really means is the robot needs to protect against anywhere the human might go, which is formally called the forward reachable set. Now, this does make robots safe, but unfortunately also makes them incredibly and annoyingly conservative. So here we have a robot whose goal is behind Ellis, and Ellis is just going to be walking around slowly and minding his own business. But this poor robot essentially thinks that Ellis could go anywhere. And by defending against the full forward reachable set, the robot is protecting itself against this version of Ellis that could run out and try to collide with the robot on purpose. And what does this result in? Well, the robot actually ends up getting chased to the corner of the room with this kind of predictive model. And so this is clearly impractical. And yet, at the same time, it's not acceptable for robots to crash into people when their human models fail. And safety in general is incredibly challenging, if not impossible, to guarantee a priori offline. And so what's a practical notion of safety that we can embrace? Now, while this might seem hopeless, we're going to talk today about a missing piece of the puzzle that might get us one step closer. We can see this puzzle piece in this video. In the beginning, everything is going well. But as Sylvia deviates from the predictions by going around the coffee, the model is still saying that she's going to turn around and head straight towards her goal, despite a lot of evidence to the contrary. And so what's missing from the safety picture is the online data that's coming in. The key to maintaining safety while still using data-driven models is to leverage this online data to consistently monitor the prediction quality. If the person just took an action that you had assigned low probability to, and if this happens a few times in a row, then clearly you should know that something is wrong. Of course, the question is, what should you do about it? And so today I want to share with you 3 stories for 3 answers that the Interact Lab has worked on. I'm going to start with summarizing some work from Liting Sun. Litting observed that there's an alternative to these high capacity models that might have a better out of distribution property. So the alternative here would be to use planning to generate human trajectories that always stay on the road, avoid collisions, make progress, so on. And planning is really good at this. The data in this case is still useful, but not directly to learn behavior, but instead to train a reward function for the planner to optimize that explains the human behavior we observe. Now, this has no problem with having the predictions actually stick to the road and make progress along the route. However, this comes at a cost of naturalness. So here we see the planner in orange, unable to predict how wide of a turn people will make, likely because the reward function it has learned is unable to make sense of these nuances in human driving. So how can we get the best of both worlds? Well, if this is the full space of inputs we might see, and this is the training data we have, what we really want to do is use the end-to-end predictor on the common cases. But for rare cases, like if the vehicle is stopped, which we don't see often, could we somehow detect that the end-to-end predictor won't do well and switch to the planning-based predictions instead? Similarly, for inputs that are out of distribution, like a totally new exit that has never been seen before at training time. The main challenge is, how do we know, given a new input, which region this will fall into? In other words, how can we online detect that we're in a situation where we shouldn't rely on the end-to-end predictor? And this comes back to what we said before. We need to use that online data to monitor the prediction quality. And in this case, switch to the planner only when it seems like the end-to-end predictor is consistently erroneous. Now, this work performs a deep dive and an investigation on several methods for such switching, from Bayesian filters to classifiers. I don't have time to get into all the details today, but you can check out all of the cool stuff that they tried out and all of their technical findings in this work and the corresponding paper shown here. Now let's take a look at the second part of the story, which is something that I worked on during my PhD. This story is going to center, yet again, around using online data to monitor prediction quality. However, now when predictions worsen, we want to automatically decrease our trust in the model and increase model uncertainty. So consider this indoor scene with a pedestrian and a ground robot. And let's say that our model knows that people tend to walk towards this shelf over here. Regardless of whether you're using an end-to-end or a planning-based model, the predictions might be probabilistic and might employ this softmax distribution that you see here. So here I'm showing the planning-based variant with the Q function, but in general, you might have some learned potential function here. This temperature parameter here governs how optimally the human moves in the direction of their goal. In this case, in the model, the shelf. Now, what is this model really saying? It's saying that people are noisily optimizing this potential function. Now, where is the noise encoded? It's in this parameter beta, which is built into the model. Now, although this parameter is typically fixed, interestingly, changing this parameter can let us scale the predictions from purely goal-driven to that full forward reachable set. So in one extreme, if I set beta equal to 0, then I get a uniform distribution of our actions. In other words, that forward reachable set. In contrast, when we choose a large value, most of the probability mass will be on the optimal action. Our idea here is to use this built-in parameter and reinterpret it as a measure of model confidence. In other words, how much the human is abiding by our modeled objectives. Thus, instead of pre-specifying it to always have our predictions be conservative or to always trust our model, let's use data and estimate this model confidence online. So consider this simple example where you're just looking at two possible values of beta, and we're starting out with a uniform distribution over model confidence. Let's see what happens when the human moves in an unmodeled way. Let's say we observe the following action of the person moving directly away from the modeled shelf. What should be our model confidence after we observe this measurement? If we take a look at the Bayesian update, let's consider how likely is this action under each of these model confidence values. The human action is actually assigned the highest probability under beta equals 0. And thus, the Bayesian update will automatically shift probability mass onto low values of beta, as we can see here, and the predictions naturally blow up in their uncertainty. Let's see what our confidence-aware predictions look like in hardware in our running example with the coffee spill. Pay attention to the predictions visualized in the video on the right. While Sylvia moves straight, the predictions are confident, but as she deviates by stepping around the coffee spill, the confidence drops and the predictions blow up. And so by relying on our confidence-aware human model, the robot automatically plans a more conservative path around her to stay safe. I further investigated this aspect of the safety story with PhD student Thomas Tian. So safety monitors are an additional layer of safety for robots interacting in close proximity with people. These methods allow any high-level planner to guide the robot, for example, your favorite neural network planner, but compute a set of states from which imminent collisions between the human and robot would happen. Essentially, as soon as the human car reaches the boundary of the unsafe set, the safety monitor takes over control to steer the robot away from danger. Now, traditionally, to construct the set of unsafe states, the safety monitor treats the human-robot interaction as a zero-sum collision avoidance game. But much like the forward reachable set, this is often too pessimistic and inhibits the robot's ability to make progress by intervening excessively. Instead, we could use a non-adversarial human model, for example, a general sum dynamic game. However, as we've seen in this talk, our human model could sometimes be incorrect, compromising the quality of our safety monitor. So how can we automatically adapt the conservativeness? Well, it turns out that we can extend our idea of model confidence into this game theoretic safety monitor domain. By inferring how rational the human appears under the general sum game, the robot can smoothly shift between less conservative safety monitors and a full worst case safety monitor when the human model degrades. So let's take a look at a roundabout scenario where the robot wants to merge in front of the human car. First, consider a human who is behaving in a non-adversarial way. However, the robot is using a worst case safety monitor. This results in the robot executing an unnecessary safety maneuver and abandoning its original goal to merge. Instead, our confidence-aware monitor detects that the human is behaving in a non-adversarial way with high confidence. And as a result, the robot reduces the size of its unsafe set and confidently merges in. Finally, we simulated a distracted human driver who is behaving in an unmodeled way. Our confidence-aware monitor detects this as well and automatically enlarges the size of the unsafe set. Here, the robot actually executes its safety maneuver early on, accelerating out of the way of the oncoming distracted driver. Results across 20 simulations with modeled, noisy, and unmodeled humans show that our confidence-aware monitor has a 0% collision rate, intervenes only when necessary, and enables the robot to improve its overall reward during the task. We also looked at highway merging and saw similar results in simulation 2. And we finally looked at replayed traffic data. Here we saw from our experiments that human driving is closer from a safety perspective to our confidence-aware method than the traditional worst-case method. Now, there's one last part of this idea of online data and safety that I want to cover. And this is that even if you use online data and you maintain uncertainty, your robot can still sometimes be too conservative, even if that uncertainty is warranted. So let me show you what I mean. Here we see an autonomous driving scenario where the autonomous car shown in white is trying to take a left turn. There's also this human-driven vehicle on the opposite side of the road. Here the robot has uncertainty over if the human is going to go straight or left. And because it has this uncertainty, it's going to hedge against both of these here. And the conservative robot is going to protect against both of these possibilities. And in fact, what ends up happening is it ends up getting stuck. Now with our reward function here, the robot makes a little bit of progress, but then waits. But with other better planners, it might not even bother and just stay put. So you might wonder, well, this seems like a safe behavior. What's the problem? Well, what's really missing here is that even though we don't know right now what the red car wants to do, it will become clear very soon in the future. And our planning does not leverage that at all. So one approach to efficient motion planning under this kind of uncertainty is called contingency planning. Here, the robot safeguards against both possibilities for some short time horizon, mentioned here by TB. And after that amount of time, after that branching time has passed, the robot creates two contingency plans, one for each outcome, red if the person goes forward and blue if the person turns. However, the choice of this branching time is really critical. It's essentially saying that at this future time, the robot will be certain about if the human is turning left or going straight. And this is a really challenging thing to know a priori. And so in fact, in this scenario, relying on the current data we have gathered online isn't enough. We actually need the robot to reason about the possible future data it will observe in order to make a safe decision. In this scenario, the robot was too optimistic about when it thought it would have certainty about the human's intent, choosing a very small branching time TB. When the robot executes its plan, it still has uncertainty about the human's true intent when it reaches the branching point, causing the safety violation. So we know that we can't branch too early, but we need some notion of the longest time it might take to figure out the human's intent. And this is because what if the person does this maneuver where they pull all the way out into the intersection and then take a turn at the last minute, rather than clearly indicating their turn earlier? How do we reason about when we will know the human's intent in the future in these possible scenarios, and in fact, in the worst case? So here, my idea was to think of the problem from a dynamical systems perspective, where the dynamical system is not just defined over the physical state, but also over the learning parameters as well, where the online data that's coming in is a part of the controls. This goes full circle in the safety story, because now those reachability safety techniques that we had can apply, but no longer just over the physical system, but rather over this learning dynamical system. The first step in our framework is to define the joint state space Z, which includes the human physical state and the parameter estimate, which is denoted here in general by theta hat. In this example, our robot is maintaining a belief over if the human-driven vehicle is going to turn left or go straight. Next, we need to model the evolution of the physical state and the estimate as a function of the observations. And the joint dynamics here are the stacked physical dynamics of the human and the learning dynamics. And here the learning dynamics are just our Bayesian update. As you can tell, the input into this dynamical system is the data or the control actions that we observe the human take. Now that we have our dynamical system, we want to determine which human data will steer our learning algorithm into the desired parameter values we seek to estimate. In other words, if the true human intent is to go forward, then does there exist a sequence of human data which enable our robot to detect that the human actually wants to go forward? Now, this is actually an instance of a reachability problem that we can pose and solve via well-established optimal control methods. So more formally, we can solve this problem via the discrete time Hamilton-Jacobi variational inequality, whose value function can be solved for via dynamic programming. I know that this equation might seem like a lot, but just think about this as a variant of the Bellman equation that many of us are familiar with in MVPs. The key things I want you to pay attention to is that the formulation neatly allows us to encode several important properties of our analysis. First, we can encode the desired estimate inside of this function L of Z. Second is we can model the human as either a minimizer or a maximizer of our analysis objective, and this allows us to simulate different strategies in which the human generates data. Min means that the human is generating data cooperatively. For example, the human is trying to help the autonomous car infer that they're going forward as fast as possible. In contrast, Max models the human as an adversarial data generator, meaning the human wants to deceive the robot for as long as possible about their true intent. These mins and maxes let us obtain the best case and worst case answers to our queries. Finally, U is the set of all possible controls, i.e. data that the human could generate. We can then compute this value function and use it to extract our desired quantity, t worst, which is the slowest time it could take our robot to infer the human's intent. Intuitively, we can now use our tool to compute the worst case time to learn for each outcome. Time to learn in the event the human is going forward, and time to learn in the event that the human is turning. The safest branching time will be the max of these two inference times. We want the robot to hedge its bets until the hardest of the two inference outcomes happens. Now, choosing this safe branching time ensures that the robot commits to a contingency plan only after it has certainty, balancing safety and efficiency. And so here we can see the final trajectory planned with this method, and the robot can effectively make progress to the intersection while also avoiding collision with the robot or with the other human. So we ran a series of simulations comparing a safe motion planner, which always safeguards against both hypotheses equally, a heuristically chosen branching time, and our worst case branching time that is generated by this optimal control method. For all planners, we varied the initial conditions and the goals that the simulated humans were moving to. The results demonstrate that our worst case time to learn framework enables the robot to make safe and efficiently goal-driven plans, even with a uniform or incorrect prior over the human's intent. Now we can actually use the same exact framework and key idea to answer other interesting questions about our human models that are adapting online. So we just saw how to design safe but efficient motion planners via the worst case time to learn, but we can also gain insights onto environments that are challenging for intent inference, automatically generate informative and deceptive human data and behavior, and we can determine effective initializations for gradient-based learning. Ultimately, all this work has been in an effort to generate practical notions of safety for close proximity human-robot interaction. The core idea is to leverage the online data that we are or we will be observing to modulate the conservativeness of robot interactions with humans. With that, I want to thank my advisors and collaborators, and I'm happy to take any questions.
Thank you, Andrea. Do you have any questions? I have a question. So essentially your methods work by modeling uncertainty of the human, right? But if you were to deploy this system in a real car, in a real robot, this uncertainty would be compounded by the uncertainty on actuation, uncertainty of perception, and so on and so forth. And all this accumulation of uncertainty is usually a big problem because it gets untrackable really quickly. What's your opinion on that? Do you think it would be a problem in your case? Do you have mitigation strategies? What's your opinion?
Yeah, that's a really, really good point. And I personally haven't investigated this with the techniques I presented today. Typically in the techniques I presented, we assumed very high quality state estimates from something like a motion capture. But in reality, that's absolutely a really big concern. The other interesting concern that I think is also worth talking about is how do you leverage probabilistic predictions in the first place? Like even if I can capture all the uncertainty, maybe it's blowing up, being able to leverage that properly is also, I think, still quite challenging. There are a lot of methods that have been developed, and I think that each of them have different sort of strengths and weaknesses. I don't have a silver bullet answer to you, if I'm being very honest. I mean, I think that this is just a very big challenge. Some of the things that I think are interesting to investigate include preserving sort of these models of uncertainty all the way through and seeing how bad that they are, especially if you can calibrate your models very effectively. It might be good to propagate that uncertainty and have it truly be represented. Of course, the big question is, how do you calibrate your uncertainty models in the first place? So that's a big open challenge I think is very interesting. Alternatively, the other kinds of approaches that I have worked with are, again, taking this more like robust perspective and saying, well, I don't exactly know the right kind of distribution that my sensor data is coming from, or the kind of distribution for my predictions. So what if I bound or like over approximate for example, the initial conditions where an agent can start from, and then use that to propagate plans or predictions in the future. It's also very conservative, but maybe you skirt the issue of having a poorly calibrated model a little bit. But those are some directions I think are really interesting.
Thank you. Any other questions? Okay, so that's all. Thank you. Thank Andrea again.